In today's video, I'm going to teach you how to create a power supply design spec for literally any application. We will go through all of the information you need to know, including a step-by-step walkthrough of the actual template I use to create my own power supply design specs. But real quick, before I go any further, I encourage you to check out the description. There will be some links there that you will probably find helpful. And with that out of the way, let's get right into it. So first, let's give a little background on the power supply spec sheet. Every good power supply design begins with a document known as a specification sheet or spec sheet. This details all of the engineering requirements for the design and gives you the information necessary to do all of your component calculations. There are a bunch of different formats for these spec sheets, and you'll probably come across a wide variety of them throughout your career. But today we're just going to focus on how I like to do my spec sheets, which uses a Microsoft Excel table. There are quite a few different parameters you'll need to be familiar with when specifying a power supply design. So we're going to go through all of those in extreme detail and give you a thorough explanation of them. Okay, so what we're looking at here is my power supply design spec sheet template. I have organized it by different topologies, but there are a lot of similarities between the sections. Using the buck converter template as an example, let's start with an overview of the table. So the leftmost column will be the list of all of the different design parameters for our power supply. These are going to describe the specific metrics that characterize and describe the performance of our design. The next three columns over, we have what is the minimum, typical, and maximum expected value for each of those parameters. Power supplies and all electronic circuits in general typically operate within a certain range of values for a parameter. So it's a good idea to specify those ranges in our spec sheet. Then the last column on the far right is going to be the units. And this is just a way of being thorough and making sure that we're not accidentally designing a power supply to handle 500 amps when it really just needs to handle 500 milliamps. Okay, so now let's dive into those individual parameters we talked about. The first one is the input voltage range, and this one should probably be pretty straightforward. This is going to be the range of voltages that our power supply can handle on the input. In the example of the buck converter, we know our output voltage will be lower than our input voltage, so our minimum input voltage will have to be something that is higher than our output voltage. Depending on your application, your input voltage could be something that it varies quite a lot, or it could be constant for every configuration of the design. Let's take an external 12-volt brick as an example. In theory, we can expect our input voltage to always be 12 volts. But it's always a good idea to design with some margin in case there is some slight variability with our 12-volt supply. So what I would do in this case is specify our input voltage range to be, say, 10 volts to 14 volts. That way we have some margin on each side of that 12-volt nominal input. There are other cases where you may want your power supply to be able to handle a wide range of input voltages, and that is also perfectly acceptable. For example, you might want your power supply to be able to handle a 12-volt input as well as a 24-volt input. So that is perfectly acceptable to design with that wide of a range. The general takeaway here is to make sure you have enough margin on both the minimum and maximum input voltage ranges so that your design operates safely for the majority of cases. The next parameter is the output voltage. And just like with the input voltage parameter, the output voltage will have a nominal value that we specify based on the requirements of our application. One very common example you will see is 3.3 volts, which a lot of digital circuits operate at. Ideally, we would want every single power supply to output exactly 3.3 volts. But unfortunately, that is just not feasible or realistic due to a variety of factors such as temperature, humidity, manufacturing tolerances, and more. So instead, we need to specify an allowable voltage range for our power supply to output. A typical sort of industry standard is about 3% of margin on each side of the nominal value, meaning that if our specified nominal output is 3.3 volts, then we would expect our design to output anywhere from 3.2 volts to 3.4 volts. That 3% value is not a strict rule. In fact, you can have your tolerance be whatever you want it to be. That is just a common number you'll see throughout the industry and other, design specs. Another note on that is it can actually vary by topology. For example, a flyback converter might have a 5% tolerance, while an LDO might have a 1% tolerance. So it's also based on what the reasonable capabilities of a given topology are. The next parameter is the output current, and this refers to the maximum amount of current that the power supply can provide to the load. This value is usually determined by doing a power budget analysis on the rest of your design and determining what all your power supply has to power and the total current you expect those systems to draw. For example, let's say you have 3 subsystems in your design that all require 3.3 volts to operate. Subsystem A might draw 100 milliamps, subsystem B might draw 350 milliamps, and subsystem C might draw 200 milliamps. So the total expected current draw of your 3.3 volt power supply is going to be around 650 milliamps. And for the output current parameter, it's okay to just specify a maximum output current, as any value under this will typically be, it'll work. It'll be acceptable and your design will be able to meet the other performance requirements that you specify. I will put one caveat here, and that you will see some power supplies have a minimum output current requirement, and that just has to do with their ability to regulate a steady output voltage under light load conditions. But that's a more advanced topic that we will cover in another video. For now, just worry about specifying the maximum output voltage. And just like with our input voltage and output voltage, it's usually a good idea to have some margin for your output current capabilities. So in the example where we talked about having 650 milliamps of expected current draw, adding about 20% margin is not a bad idea. Another thing I'll note is if you multiply the maximum specified output current times your nominal output voltage, you get the power rating of your power supply. For example, if that 3.3 volt power supply that we were just talking about is rated up to 1 amp, then your power supply is rated at 3.3 watts. The next parameter is the switching frequency, and the switching frequency is an interesting parameter. The switching frequency refers to the rate at which the MOSFET switches on or off, and there is a whole lot of theory behind choosing a switching frequency for your power supply, and it actually affects many different areas of the design. For this video, I'm just going to touch on a few key points. I'll cover more advanced topics in later videos. So typical switching frequency ranges vary depending on which topology you're using, and they can range from tens of kilohertz up to 5 megahertz or more in some cases. The general trade-offs with switching frequency are size versus efficiency. By choosing a higher switching frequency, you can select a smaller inductor and capacitor. But because your MOSFET will be switching at a higher rate, it will dissipate more power in what is referred to as the MOSFET switching losses. A higher switching frequency will also yield a better transient response. So parameters such as your load step and overshoot can be reduced with a higher switching frequency. But those really aren't that important. A lower switching frequency, on the other hand, will cause your MOSFET switching losses to go down. But the cost is going to be you'll need a much larger inductor and capacitor. And again, it's also going to have a slower transient response, so your overshoot and undershoot will probably be a little bit larger. For buck converters, switching frequencies typically range from around 300 kilohertz all the way up to 3 megahertz. A good value for most applications is in the 1 megahertz range. If your power supply needs to be able to supply a lot of current, then I recommend choosing a lower switching frequency, because efficiency is also directly tied into the thermal performance of your power supply. And more efficiency means better thermal performance. And that is a great segue into the next parameter, which is going to be the efficiency. Efficiency is one of those parameters that could be super important for your application or not really important at all. For example, if your device needs to be battery powered, you'll probably pay close attention to your efficiency because that can significantly affect the battery life of your device. And one other thing to note is different topologies will have different anticipated efficiencies. And even within a given topology, there are other factors that can affect how efficient the final design is. For a buck converter, typical efficiencies range from about 90% to 95%. There will be another video where we do a power loss analysis of each topology. So you will be able to see the places where you can sort of optimize your design for efficiency if you want to. The next parameter is the output ripple voltage. The output ripple voltage refers to the small AC component of the output voltage that is due to the rapid switching of the MOSFET. It is actually very important to limit your output ripple voltage because too much noise on your power supply line can negatively impact the performance of the devices that it powers. Like with other parameters, the maximum allowable ripple voltage can also vary depending on what topology you're using, as well as some other performance conditions. For example, with a buck regulator, it is very common to see a maximum ripple voltage spec of around 0.5%. So in the 3.3 volt example, that is a total ripple voltage of around 16.5 millivolts measured peak to peak. The next parameter is the inductor ripple current, and that is a very interesting and critical parameter to specify. This parameter is usually expressed as a percentage of your maximum output current, and it is essentially a measure of how much the current through the inductor varies during operation. We will use this parameter to help us calculate the peak current through the inductor, which is critical for speccing our inductor because it tells us what its saturation current rating needs to be. There are some minor trade-offs when specifying the inductor ripple current, and we'll get to that in a later video. But typical values for the percentage of ripple current is around 20 to 40% of your maximum output current. Now, it's also worth noting that not all topologies have an inductor ripple current spec, but it's still important to know because a lot of them do have it. The next parameter on the list is going to be the overshoot, and this refers to how much the output voltage overshoots or goes above our specified nominal output voltage during startup or variable load conditions. Too much overshoot can damage the electronics that are being powered by this power supply, so it's important to specify a maximum allowable value. Common value you will see for overshoot is going to be around 6%. So in the example of the 3.3 volt buck regulator, a 6% overshoot will yield a voltage of around 3.5 volts maximum. And then the final parameter on our spec sheet is going to be undershoot. And this is exactly like the overshoot parameter we just talked about, except for in the opposite direction. Output voltage undershoot typically occurs when there is a very abrupt and significant change in the amount of current that the power supply is needing to source. For example, let's say you turn some subsystem on, there will be a very momentary and brief sag in your output voltage as it has to correct for the increasing load requirements. Just like with the overshoot parameter, we want to make sure that our output voltage does not sag too low because other systems that are connected to it will also have a minimum voltage requirement, and if it sags too low, those could go into some type of shutdown and that could just ruin the functionality of our whole device. Just like with the overshoot parameter, a typical undershoot value is around 6% of your output voltage. So in the case of the 3.3 volt power supply, we would be looking at around 3.1 volts as our minimum undershoot voltage. And that is pretty much everything you need to know about creating a spec sheet for your power supply design. If you have any questions about these parameters or anything related to creating a spec sheet for a power supply design, please leave them in the comment section below. I respond to every single comment. And so thank you if you made it to the very end of this video, and hopefully I will see you in the next one.